It's the product rule. If I don't see a sum, it makes no sense, right? So we apply natural log as you did. So I would denote this by y, the square root of x raised to natural log of x squared plus 3. Yes, I have to apply natural log. Natural log y will be natural log of the square root of x raised to this power. Yes, I have to bring it down. So it's natural log y equals natural log of x squared plus 3 multiplied by natural log of the square root of x. And now when you differentiate 1 over y times dy over dx, if you do not write a sum, I can't give any credit. It's the product rule. So first function, second function. So you have to write the first function prime times the second function plus the first times the second function prime. If I don't see a sum, it makes no sense. Are all these steps clear so far? Yes, Thomas?
How did you get 1 over y? Oh, it's okay. So the derivative of ln is 1 over y?
Yes, from Monday. 1 over y times the inner function prime. So let me write this again, and I'll come back and finish that. So natural log of u prime is 1 over u times u prime. If it's x, then x prime will be 1. So now we come back. So this is 1 over y, dy over dx. 1 prime is this, 1 over x squared plus 3 times 2x multiplied by natural log of the square root of x plus, I always run out of room, of course, plus 1, which is natural log of x squared plus 3 times the second function prime, 1 over the square root of x, times the inner function prime, which is 1 over 2 the square root of x. So I'll copy everything one more time. I have dy over dx. And now I can multiply both sides by y, and I'll put it outside. The square root of x raised to natural log x squared plus 3 times. This I cannot do anything to, so I'm going to write 2x natural log of the square root of x over x squared plus 3 plus natural log of x squared plus 3 over 2x. And you don't have to do anything else to it. So one more time, when you apply natural log and you bring the power in front, this becomes a product. And when I differentiate a product, I have to use this in any order you want. You can reverse this, you can reverse this, whatever you want to do. But you cannot write 1 prime times 2 prime. If you write 1 prime times 2 prime, then I can't give any credit. So one or the other. And in this case, you can even reverse these. Doesn't matter because it's plus. You cannot do that on the ratio because it's minus. So I like to write this one more time. It's just a habit. 1, 2, 1, 2. 1, 2, 1, 2. But it's up to you. It's really not important. So we differentiate, and I have to have a sum. If I don't see a sum, then something is wrong. Any questions? Is this okay? Okay. So back to what we're doing. Let's work on one more problem, and then continue with 3.10. I don't want to postpone the test too far out because I still have chapter 4 and chapter 5. At the end of this week, we are down to 8 weeks. So 8 weeks left, out of which the last week I do not count on because I have to review everything from scratch. So we're down to 7 weeks, out of which we have 2 more tests. And I review and then the test. So I'm down to 5 weeks. So in 5 weeks, I have to talk about chapter 4, which is also a big chapter, long, and chapter 5. So in 5 weeks, I have to finish these. So meaning in 10 hours. I mean meetings, not hours, sorry, meetings, 20 hours, roughly. So that's why I don't want to postpone it too much. But I don't think we're ready for Wednesday. I don't think so. We need more practice. Maybe the entire week next week we're going to review for the test. But again, then I will be down to less than 5 weeks for these 2 chapters. And this is a huge chapter. This has only 5 sections, but this one has 10.
Can you stay after class on that exam day to continue the chapter?
You mean at the exam day?
So if we're not doing the test on Wednesday.
So we'll see. Let's see what we accomplish today, and let's discuss the whole thing again on Monday. It depends on also what you do between now and Monday. Because if you do nothing, then... So it all depends on that. So let's work on this problem. And then we'll go back and... as I mentioned in 3.11, I just want you to remember 3 functions and their derivative. Not their inverses, nothing else. So just 3 functions and derivatives of those functions. And here, this is a section that it really shows how powerful calculus is. So this was invented before calculators were invented. So they were able to approximate tangent 44 degrees by hand with calculus. Nobody could have done that without calculus or calculators. So this is very important, 3.10. Okay, so let's work on another problem. And then we'll make a decision again on Monday or at the end of the class, we'll see, okay? So that's why this is what scares me. The fact that we are down to 8 weeks, I cannot consider the last one, and 2 more weeks will be 2 more tests. Then we have Thanksgiving, right? And we have to recover that. I have to give you those 2 hours. Remember Wednesday night before Thanksgiving, we're closed. So that's why we recovered. I gave you back the Labor Day, and I have to also meet with you to recover that. I can't miss that. Because then I'm down to 3 weeks, roughly, to finish 2 chapters, and I can't do that. So we'll have to set up a time again, and I have to give you those 2 hours back that we lose because of Thanksgiving. Okay, so let's read this problem. A boat is pulled into a dock 8 feet above water level by a rope attached to the boat at the water line. So I envision this okay, so here's the rope. Here's the boat. And here's the dock, of course. Okay. It says a boat is being pulled into a dock 8 feet above water level by a rope attached to the boat at a water line. So that's my mistake. So I shouldn't be, you know, it has to be at the water level, right here somewhere. Not this. Right? A rope attached to the boat at the water line and running up to the dock. Okay, so that's the situation here. Because I showed the water there, so I have to connect the rope at that level. If the rope is being pulled at a rate of 2 feet per second, so this 2 feet per second. How fast is the boat approaching the base of the dock when the boat is 6 feet away from it? So this is what we're interested in. Rate of change of this when I'm going to call it X, is 6 feet away. So it's 6 feet. So let's read the problem one more time. A boat is being pulled into a dock 8 feet above water level. So this is 8. Make sure I put everything, all the information in there. By a rope attached to the boat at the water line and running up to the dock. Here it is. If the rope is being pulled in at a rate of 2 feet per second, so this changes at 2 feet per second, how fast is the boat approaching the base of the dock when the boat is 6 feet away from it? How fast is this changing, specifically when X is 6 feet? So any ideas here? Any suggestions? Any ideas? Yes. Which would involve, so I have this as X. I have to denote this, let's say, as W. And I have a right triangle. Can anyone give us the right triangle, Pythagorean theorem in this right triangle?
X
Yes?
plus 8 squared
Yes?
is equal to W.
Good. So what are we asked to determine? No.
The rate of change of X,
So dx with respect to
dW,
time. It's feet per second. What is given in the problem? Okay, so this is our question. When X equals 6 feet, what is given in the problem? What does this represent? Yes, of what? What does it represent?
dW
Very good. dW over dt. Good, so how do I proceed? I identified what is asking me to do. I identified what is given in the problem. I have an equation, and how do I continue? What do I have to write? What will I do? Yes? In order to determine this, what should I do to this equation? Good. I don't solve it. That's not what I meant. I meant this. Okay. What is the left-hand side? Yes? Excellent. 64 prime is 0. And the other side is 2 w dw over dt. I will divide both sides by 2. From this equation, I solve for what I'm interested in, which is dx over dt equals w times dw over dt over x, when x is 6 feet. Perfect. So now, what do I do next? I replace this by, good. I replace this by, and I replace this by, I go back here, now I solve, because x is 6 feet, so 36 plus 64 is, yes, so 36 plus 64 will be w squared. From here, I know that w must be 10. So I simplify. So this is 10 divided by 3 measurement unit. Excellent. So here's a scenario. One more time. I pull the boat. And I pull it at 2 feet per second. This rope changes its length at 2 feet per second. And since this should be negative, they should be negative, let me see, It should be indicated here because the rope, yes, the rope, the rate of change is negative because the rope becomes smaller and smaller. Also, how fast is the boat approaching the base of the dock when the boat is this? So also the rate of change of this is negative, of the x, because x is getting smaller. So the rate of change is also negative. So I will put negative here and negative here and negative here, as well as because this is negative. Okay, negative, because it gets smaller and smaller. So one more time. So I pull the boat. The rope gets smaller and smaller. The length W gets smaller and smaller. So the rate of change is negative. And at the meantime, the boat gets closer and closer to the dock. So at the instant at which the boat is 6 feet away from the dock, the rate of change of x is negative 10 over 3. Negative 3.333 feet per second. Now, this section is full of all sorts of problems, all sorts of concepts. We can work on another problem. Let me finish section 3.10 and then we'll go back and do more from here. Okay, so I gave you this handout last time, 3.10. So let's talk about linear approximations. There are several concepts in this section. So 3.10. We will talk about differentials. Like dx, dy. We are going to talk about linear approximation of a function near a value. Linearization of a function near a. So let's start with the concept of linear approximation, and the linearization. Okay, so let's start with that. Back to our graph. You must be tired of this graph by now. Here's a function f of x. I have a point on this function. I bought a new set of markers. Let's see what I have here. Okay. So I have a point P of coordinates a comma what? Very good, f of a. And let's say I draw a tangent to this graph at that point. Can anyone give us the slope of this tangent? I have f of x, I have the point. How do I determine the slope of the tangent at any point? Right, but now I have rules. Say it again. Not f of a. No. How do I determine the slope, the rate of change, the slope?
F prime of A.
Thank you. Of course, it's f prime of a, right? The slope, the rate of change, right? So I have a point and I have the slope. Is there any way I can find the equation of the tangent? not really. Okay, anyone else? Right. So y minus y1 equals the slope times x minus x1, where a is x1, y1 is f of a, and the slope is f prime of a. Right? Thomas, is that okay?
You only know one point.
Right.
So,
But I also know the slope of the tangent.
alright.
So then I have y minus f of a equals f prime of a times x minus a. And I'm solving for y. So this is f of a plus f prime of a times x minus a. So this is the equation of this line that is tangent at a, that a comma f of a. Would you agree? Okay. Assuming I change the point and I'm here now, let's say, and this with point Q, and I have a different x and a different y, do you think that this equation of the tangent here will be the same with the equation of the tangent here? Absolutely not. Is that clear? And then even the slope is the same. This is much more acute, much higher positive slope. This is much less, right? Less. So then this equation, of course, changes as the point moves on the graph. Would you agree? Okay. So now if I'm looking at an interval very close to P, so a tiny interval very close to P. So if this is 5, like between 4.8 and 5.2, very close to 5, do you think that if I use the line or I use the function to evaluate, will that be a big difference? No, because they're very close. So that's the reason why we will say that L of x equals f of a plus f prime of a times x minus a is the linearization of f of x near, this is a key word, near a. In other words, in a small open interval around a. So coming back to our handout, the linearization, if you want to fill it in, f of a plus f prime of a times x minus a. Why? Is because we can say that f of x is approximately equal to f of a plus f prime of a times x minus a, of course. So this is the linear approximation of f of x near a. So now let's look at these two examples. We are given a function which is f of x equals x squared. And I'm told to find the linearization, which is the function for the given function with x near 1, and then when x is near 2. So first, near 1, and then later, near 2. So the linearization is L of x equals f prime of 1. I'm sorry, I meant to write f of 1 plus f prime of 1 times x minus 1. I will delete out. So f of 1 plus f prime of 1 times x minus 1. Can anyone give us f of 1? Good. Can anyone give us f prime of x? Can anyone give us f prime of 2? X minus 1. Perform the calculations. 1 plus 2x minus 2 equals 2x minus 1. So near 1, function x squared can be approximated by 2x minus 1. Can anyone dictate near 2? How do I find the linear approximation? Near 2. It has to be a totally different line. What do I write? F of 2 plus f prime of 2 times, of course. So can anyone give us f of 2? 4 plus f prime of 2. Good. Times x minus 2. Combine like terms, distribute. 4x minus 8, so 4x minus 4. And as expected, at 1, there is a certain function that approximates x squared. At 2, there is a different linear function that approximates x squared. Easy enough? Say it again. Okay. So find the linearization and the linear approximation. They are the same of f at a. So let's choose one or the other, whichever you prefer, and you can do the other one. A. Okay, so let's work on A. Any questions so far? Pretty easy, right? Okay, this part is good. So we want to look at f of x, which is 1 divided by the square root of 2 plus x at a equals 0. So the linearization will be, let's write the formula first. What will I have to write? Tony, are you okay?
Yeah.
F of 0 plus f prime of 0 times. Good. So now let's go back. Change f of x into 2 plus x to which power? Negative. It has the square root. It cannot be negative 1. Negative 1/2. Very good. So then f prime of x, I bring negative 1/2 in front. I have 2 plus x raised to which power? Say it again. Very good. Negative 3/2 times the inner function prime, which is how much? The inner function prime is 1, the linear function. What is the slope of this function? 1. Good. So this is negative 1 over 2 the square root of 2 plus x to the third. Are we okay so far? Any questions? Please stop me if you have questions. Okay, so let's determine here f of 0. How much is f of 0? This is the function. We have to plug in 0, so we get it's the square root.
Yeah, 1 over 2.
Okay, yes, I didn't hear that part. Sorry about that. Okay, so now let's find f prime of 0. Negative 1 over 2 is 2. 2 plus 0 is 0. 2 to the third will be 8, but I have to change it into 2 the square root of 2. So this will become the square root of 8, which is the square root of 4 times the square root of 2, which is 2 the square root of 2. So f prime is -1/4 the square root of 2. So all I have to do is put everything together now. So L of x equals f of 0 is this, minus 1/4 the square root of 2 times x. There is nothing else I can do here. So this is the linearization. And the linear approximation is the same thing. It's approximately 1 over the square root of 2 minus 1/4 the square root of 2 times x. Linear approximation. So this means, one more time, that this function near 0 can be approximated by this line. So if you want to determine, so evaluate this function at point 1, and you plug it in, or you plug in here point 1, you should get very similar results. And we can do that with the graphing calculator. So I have two functions. Okay, one function is 1/2, so it's 1 divided by the square root. Did I do something? Okay, 1 divided by the square root. I will put parentheses, 2 plus x. And then I want to put in the 1 over the square root of 2 and plus, no, minus, I'm sorry, minus, in parentheses, 1 divided by 4 the square root of 2, 4, and further divided by the square root of 2. Be very careful here. And x. And now I want to go to second and table and plug in numbers. It's already there. So 0.1, 0.69 with the original function and 0.689 with the line. 0.2, 0.67 with the original function and 0.67 with the approximation. 0.3, 0.4, 0.7. So at about 1 left or right, it starts departing some, 0.6 versus 0.58. So the line is a very good, also the other side, negative 0.1, negative 0.4, negative 0.7. So still very good approximation. Using the line or using the original function, not too far from 0, doesn't make much of a difference. So that is the linear approximation or the linearization of this function near 0 only. Okay. Any questions? Any questions? Okay, so we have to come back now to the same graph over and over. Sorry. So let's go back to our graph. Here's the function f of x. Here's the point P. And this is x. And this is good. And I am going to present another point, let's say Q. In my graph, P and Q are extremely close. P and Q are very close to each other. Very close. Okay, So now, what is this? You could say h, or I could say delta x. Delta x is a minor change. It could be on the left hand side, it could be positive or negative. Minor change in x. Okay. Can anyone give us the coordinates of q?
X plus delta x.
Thank you very much.
And the f of x plus delta x.
Awesome. So then what do I have here? What is this height? Perfect. So delta y, which is f of x plus delta x minus f of x, is the corresponding what? Change. Very good. Change in y triggered by exactly by delta x. Delta y happens because delta x happened. Now, also it's very important to write that delta y is the I'm missing a word there. Which word is missing? What do you think? Give it a shot. Delta y is the value of the change. Exact. No approximation whatsoever. No approximation whatsoever. Which of these two was no approximation whatsoever? Y1 or Y2? Y1, because I used the function to evaluate. This is an approximation. It's a very good approximation near 0, but this is the exact. Okay, perfect. So then delta y is the exact value of the change triggered by delta x. Okay, stay with me, please. Here's what I'm going to do next. What do you think I'm going to do next? Because we've done this over and over. I'm going to draw the okay, let's go back. What did I always draw in these situations? The tangent, of course, at P. Here's the tangent at P. I'm going to continue this line horizontally. I am going to continue this line vertically. And now you'll tell me what I created here. What did I create? I created a
Right triangle.
excellent. One more time, what is this piece? Not till here, but till here. What is this piece? Right, the exact one, which is? Good. Perfect. Okay, now, can anyone give us the slope of the tangent line at P? Slope of tangent line at P is
F prime of X.
thank you very much. Good. Now, I have a piece here that I am after. This, I'm trying to identify this piece. Now, I know that the slope of this line is f prime of x. Now, from this right triangle, there is another way of determining, I can use to determine the slope of this line, right? What is this? I'm going to call it rise. Over what is this? I'm going to call it run. Delta x can also be denoted by dx. These are interchangeable. So delta x is a minor change in x, also denoted by dx. So then I don't know what the rise is, but I know what the run is. It's dx. Now I'm asking you, look at this, analyze it for a second, and tell me what to put here. We've seen this notation many times before. We use it in logarithmic differentiation, in implicit differentiation. Thank you. There is nothing else. So therefore, this is what is called the differential of y. This is the exact difference in y. This is the approximated difference in y. So dy equals the differential of f of x from this proportion, y prime, f prime being dy over dx. Can anyone solve for dy for us? So the differential of f of x. So dy equals, so the equation is f prime equals dy over dx. And I only want you to solve for dy. What will you say? Dy is the same with what? Excellent. Multiply both sides by dx. This is the approximation. Delta y was the exact value created by the delta x. But this is the approximated value of the change. Not the exact, but this is the approximated. So I will say dy is approximately delta y. So dy is the approximated, not the exact, change in y produced by delta x or dx. And dx is called differential of x. But remember the little note that I put here? So if Q is so close to P, very close to P, what do you think about this? Will this be a good approximation of this if Q is right here in the vicinity of P? Do you think that these two will be very different in numbers? No. They will not. That's why we wrote that the differential of y is approximately delta y. They're very, very close. So now from here, a very important result will follow. Very important result. So bear with me. tell me I would like to start here. I would like to write delta y, it doesn't matter, dy. Okay, so can anyone dictate delta y? F, yes, I'm going to replace it now with the x, minus f of x, very good, is approximately equal to, I have to replace dy by, very good. And now I'm going to add f of x to both sides. So then f of x plus dx approximately f of x plus f prime of x dx. Super important result, and I'm going to show you an example right now. Very, very important. So, on the handout, I would like you to write what dx represents, what dy represents. So you have them, delta x, delta y. Find the differential of the function. I'm going to come back to these examples in a second. Let me see the time here. Okay, maybe it's the time.